Hey, welcome back to Introducing Calculus. Hey, I've got some interesting upper and lower rectangles drawn here. I've got a little exercise for you. I want you to pick out all the lower rectangle diagrams and label them from 1 to 4. And then I want you to pick out all the upper rectangle diagrams and label them 5 to 8. Obviously there's 4 of each. Okay. So you might like to pause the presentation now and just see what you think about numbering those and have a go. Alright, I'm going to come back now and show you what we might do there. If you look at the lower rectangle ones, let's have a look here. There's one. I think this is another one. This is another one. And down here, gee, it's hard, isn't it, here? I don't know, maybe I think this one here. Okay, so could we label them 1 to 4? Why would we? Well, let's do it in increasing accuracy of estimating the area under the curve. So this is number 1. This is least accurate. This is number 2, bit more accurate, more rectangles, less actual gap between those sums and the actual area. This is even better. And hey, this is like making a whole mass of rectangles, making one whole out of all of them. Okay, so all the others are upper rectangles. So let's keep our numbering going. Number 5 here is the least accurate measure. This is the next accurate measure. And then this is the next accurate measure. And hey, this has just made one whole or mass of all the rectangles. So, you get the idea. We can keep improving this estimate. And we're en route to saying, hey, how can we actually work out that area exactly? We still have that challenge ahead of us. Okay, well, let's come down and have a look at the numbers here. When we had 4, so each of these, this is a summary now of the answers to those rectangles up there, if you like. When we had 4 rectangles, n was 4, lower sum, upper sum, average. So that's one way of estimating the area underneath. You can average them, add them up and divide by 2, somewhere in the middle. That won't always work, of course, because the curve won't be perfectly between the upper and lower, so halfway between those, but that's one estimate. Can you see as we go down here, the upper and lower sums are getting very, very close together. We're zeroing in nicely on this area under the curve. It's still not accurate though, is it? It's still a question mark over this average, is how accurate that is. Okay, so a bit of frustration there. But to improve the estimate, what are we going to do? Improve the estimate. The way we're going to do that by increasing the number of rectangles, or we could say same thing, that is smaller rectangle width across the interval. Okay, so keep that in mind. That's very important in this course to see that that is what's going to happen with our estimate. Okay, let's come on down and have a go. Here are some problems now. And what I'd like you to do in a minute is to pause the presentation and have a go. You can see here what we've got is 5 decimal places and the following functions here, a lot of functions here. what we've got to do is use technology here with the program. You can use the Casio program. Check that in Hayes and Harris, but your teacher may give you a program which will be easier to use. So we're going to come up with a conjecture here, down here I think, about the size of these values and so on as you increase the number of rectangles. So come down here a bit, there's question 3, and then I want you to, we'll just bring the answers up here, check whether on your calculator you got this set of answers. We'll stop there for a minute so that you can pause that and then go on. Coming down here in number 3, there we are. So I'll return you back up here to these problems, all calculator problems now. Do all the upper and lower sums on the calculator. Here's one here, question 3. Be careful there, and see what you think. I think there's an interesting one here. They work the area out using geometry. That's not a bad idea. That's interesting. All right, so pause the presentation and we'll put it back up here and have a go, and then we'll move on. This is quite a long presentation, so you might have to come back and do it in stages. Okay, I'm going to go on now. So we'll do a little bit of theory here and do some maths on it. If you might notice here that we've done it in very mathematical terms, this upper and lower sum. So what we're going to do here is look at, with the lower sum, what are we actually doing? We go into an interval, and we might mark that interval there. And the lowest point for the lower sum, the lowest point across the interval, we take it there and draw it across to the next point on the interval. With the upper sum, we go to an interval, like here and here. We take the highest point, see that there, and draw it back to the end of the interval. Okay, so it's a slightly different procedure. Go to an interval, choose the end, which is highest if you want the upper sum, and draw a straight line across to the lower, and that will be an upper sum. And if you want the lower sum, to draw a rectangle, go to the interval, go to the lowest point, and draw straight across to the upper part of the interval. Now, mathematically, what are we doing? Well, we're going to multiply by the width of the interval, and they're all going to be equal. We've said they're equal. So delta x means the difference in. Delta is a Greek capital for D, and it stands for difference or change in. So here, all these little gaps are the same. We're going to make equal intervals here. So what are we going to do to find the rectangle sum symbolically or algebraically? Well, here, this one, what's the height of that? F of x naught, 0, the original x. And then the height of this next rectangle is f with x1 subbed into it, and so on. So do you understand this? We're going to start at the first x, sub it in, second x, so these are the heights of the lower rectangles, third x, each time multiplying by the same width, length times breadth. How far do we go? Well, we don't go right up to the end, do we? Because the height of the last rectangle is f of the x, which is 1 back from the last, call this xn here. Okay, so there's our formula. And delta x is actually the length of the interval, the top x minus the bottom divided by n. Split it into equal parts. Have you seen this notation before? The sigma is a Greek capital again, which is equivalent to saying it's the sum of. So we're going to sum up all the rectangles. That symbol there says we're going to sum the rectangles from I as 0 to n take 1 of fxi. So in other words, we're going to stick different x's in there. Call it xi. We're going to start at 0, x0, x1, x2, and add them all up. And you might study this line as well, same idea, only of course the first rectangle starts in here at x1. Because remember, drawing the upper rectangles, you go to the interval, go to the highest end of the interval and draw back. So here it goes up to f of xn. So you've got to go right up to the end here and draw back. So the inequality statements are interesting. If you're going on with maths, it's important that you try to understand that. Okay, and the book there has got a little statement about delta x, meaning a difference or change in x from the Greek capital. Okay, so some interesting things here. B take A is always fixed. We always have a closed interval there from one end to the other, so that's the length of the interval, if you like, for which we're trying to find the area under the curve. There exists a unique number here, so we're saying, we've said this before, that A, the actual value we want, is jammed between the lower and upper sums, and we can say that if we take n very large, each of them are going to approach the same value, and that will be the value of A. So there's a way of writing that. N very large, n tends to infinity, or approaches infinity. Infinity is an abstract quantity implying the largest possible number, largest possible value or number, so you can't actually ever equal it. And the notion is it's getting as large as possible, huge. Okay, so here, this is what I want you to do here. If n tends to infinity, the lower sum tends to A, and the upper sum tends to A. You saw that in the first exercise up there, where we were looking at increasing the number of rectangles and how the lower and upper was starting to converge together. Okay, so here's our definition of A. A is the area between that and the x-axis, from x is A to x is B. That's what we're saying. We're trying to estimate the area under the curve, between the curve and the x-axis. Okay, and we've taken all curves that are above the x-axis. In this presentation, a bit later on, we'll see what happens if the curve goes under the axis. Okay, so let's have a look now at a symbol. What is A? Can we represent A with a symbol? You're still wanting to know, how can we exactly get A? Well, there was a hint back there. You could use geometry, but we'll go on. Now, this is our definition. Or, yeah, well, I suppose definition. It's a symbol for the exact area under the curve for f of x greater than or equal to 0. And here, what are we saying? This we call the integral. Ooh, did you spot that when I was talking about right at the beginning with all those rectangles? I said all the rectangles make a whole mass. Whole. Oh, integral means whole. Yes, did you see that? It becomes a mass of rectangles. It's like they're all one whole now. Right? Not quite, but it's getting there. So when it is one mass, that would be the perfect area under the curve. And so this integral actually is a stretched out S for sum of. It means the sum of an infinite number of rectangles. So it's just reflecting the estimation process that we've used. But we're using it in an exact way here. That stretched out S. And what's the symbol here? We're integrating from A to B, so that tells us what interval under which interval for which we're calculating the area under the curve. And this is saying I have to multiply the function value by the width, but we're not doing it here. This is reminiscent or symbolic of that process. So we say this is the integral of f of x from A to B with respect to x. Just reminding people that we're looking at intervals from our old rectangles going along the x line there, the x-axis. So this notation is meant to reflect the process that we're doing. It isn't the process, it's the ultimate exact answer for that process. So please remember now, this is your A. This is an estimate, this is an estimate, and if you take an infinite number of rectangles, this approaches this, they both approach the actual answer. So there's our inequality. So please remember now, this is it here. Upper and lower sums both approach, what's this? A symbol for, hang on, just get rid of that. Symbol for the exact value. Okay, for the area under the curve if it's above the x-axis there. So that's a symbol for the exact value. So when you see that, we have to try to get the exact value. All right, let's go down, have a look at an example. Sketching the graph of y equals x to the fourth from 0 to 1, divide the interval and display the upper and lower rectangles. Okay, so you actually need to be able to do this reasonably accurate. Just remembering, how do you draw the lower rectangles? Now this is from, oops, we'll have to go back up now, let's skip down. We'll come to that later on. I'll just go back up here now. I got a bit of work there. Okay, so go back up here. You go to the interval. So this is from what are we doing here? We're going from 0 to 1 and displaying it in 5 equal parts. Notice here we've got a little bit down there. We'll just click off that. So this here, where we see the hang on, we'll just get this right here. Okay, so where we see the curve is just starting there, it's crossing, getting very low there at x to the fourth, so we're having trouble drawing our rectangle there. But if you go to the interval, the idea in lower ones is you take the lower value and move it across. Hang on, I'll just go back. So, and move across. Whereas with the upper rectangle, you take the value, the higher value in an interval, and move backwards. So that's our sketch of those. And the idea, putting it in 5 parts, is to calculate that then. Now, you would generally use technology here. Generally use technology, and it asks us to do more, better estimates up to 500 here. So what would our estimate of the actual area be to 2 significant figures? It'd be, well, if you rounded both of them up to 2 significant figures, they both come to that. So we would say they're approximately the same. As we said, as n tends to infinity, the lower tends to the upper, and we're seeing it happening now. So we would say the actual exact answer of that lies between the two and would be 0.20 to 2 significant figures. Are you happy yet? I don't think so. It's still an estimate, isn't it, to 2 significant figures. Can we do better? Let's keep going and see where this leads. Okay, well, I'd like you to do some problems now. Basically, we're going to use technology throughout this. Okay. The idea at the end, when you've done the upper and lower sums, is to say, gee, I'm getting close to an actual value for that area, and remember this represents, this integral sign is the actual exact A. So we're going to start, instead of saying A equals, we're going to say the integral from 0 to 1 of root x dx equals. So this is a symbol for the actual area. Okay, so pause the presentation, have a go there, and I'll just flash down here to the answers. So you'll be able to pause that, and there's the rest of them there. Okay, so start you back up there. As you do a problem, go back, pick up the answer, and away you go. Okay, so let's move on. We've got something else here now. So if the function's above the x-axis from A to B, there's a mass of rectangles, made them all a whole, so that is summing all of them, called integration, and so this is the shaded area. This is a fundamental theorem of calculus coming up here. So it is the shaded area. We have made a complete mass, an infinite number of rectangles. So this symbol represents the shaded area in that case where the graph is above the x-axis. So they're saying here, use graphical evidence and known area facts to find this. Graphical evidence. Don't do the upper and lower rectangles. Because if you drew the graph of 2x plus 1, that's that. You could use the area of that figure there. How could you get the area of that figure? So this is the exact thing that we want. The integral from 0 to 2 means the exact area, so we're not going to use upper and lower rectangle sums here. So how can we actually find that? Well, we've got 1 plus 5 on 2. What are they doing there? Here, 1 plus 5 on 2 times 2. Okay, so how has that been the area of that? That is the area of what? Do you know? A trapezium, is it? You might check that. We're using known area facts. So here you can use that to find the area of that shape there. All right, it's what is that? A plus B on 2 or whatever, isn't it? Remember that, the trapezium, A plus B on 2. Maybe we should revise that. Area of a trapezium, A, B, and then you multiply by the height. So the area is A plus B on 2 times H, and we're thinking about that as a trapezium. The top is 1, the bottom is 5, divide by 2, and then the vertical height is that 2 there. A plus B on 2 times H. Okay, let's have a look at the other one. The other one is a quarter of a circle. So the actual area, there's the symbol for the actual area, in these cases, the integral from 0 to 1 of the function with respect to x. It's a quarter of a circle. And we know the area of a circle is pi r squared. So we can actually work it out. It's still cheating though, isn't it? It's not actually finding that area with a direct method. It's using graphical evidence and known area facts. What if the graph isn't one where we can apply known area facts? It isn't a known trapezium area or triangle area or something like that, or a circle area. Anyway, that's still a problem, isn't it? We're only going to be able to do this exact method of calculation if the area is a known shape. So let's go down and I'll get you to try these here. Use graphical evidence and known area facts to find this. And there's the answers down the bottom. So what you're looking for here, when you see this, you are saying that is the exact answer from 1 to 3 of the area under the curve or straight line y plus 4x. Okay, so we want these are exact answers, no upper and lower sums now. And you're going to have to use area facts because we still haven't found out what is a way of doing this directly. We're still relating it to geometry and using geometry to come at this. Hey, this is introductory calculus. I wonder if calculus can actually find an exact way of doing that. Well, we're going to eventually get there. Okay, so try those problems. Hang on, I'll just leave it there. Try those problems. Pause the presentation, have a go. Make sure you get those answers. You need to draw the graph and have a look. Use your calculator and look at the shape and use a formula for the area, which you know for that particular geometric shape. Okay, now there's something interesting. What happens if the curve is under the x-axis. Do you understand what that means there? F of x is less than or equal to 0. Well, function less than 0, y is positive up here, it's under the curve somewhere. It's under the axis somewhere like that. What are you going to do in there to find that area? It's upside down. Okay, so we're going to use the same idea. We're going to have a lower sum and an upper sum. And what we're going to do is this symbol still represents a mass, an integration, a making whole of all those rectangles. But what happens to it? Oh, look out. I've messed that diagram up, so I'm going to do a different one down here. Our rectangles would be upside down. Both sets, upper and lower, would be upside down. So when we do f of x, the f of x will be negative, equals a negative value. Therefore, the area will be negative. So look out, this symbol does represent that approach of the upper and lower sum to a middle value. In the case of an infinite number of rectangles, it is the exact integration of all of those rectangles, making whole. It's the exact answer. Alright? But look out, if the curve goes below the axis, it will be negative, so it won't quite be right to call it the area in that case. It'll be the negative area. So our interval will still be the same. They'll all be positives, the widths, but the rectangles are upside down, and the height of the rectangle, remember we were subbing the x value from the one end of the interval into the function to find its height. Okay, so let's have a go. Here's a problem. X squared take 1, here's the graph. It's a danger problem because it's under the axis. So our gaps here, we're going to split it into 5 from 0 to 1, so the interval is a fifth or 0.2, and then we can find the heights of all the rectangles, the upper and lower ones. So here are the heights. See, when you sub 0.2, 0.4, 0.6 in, the heights are all negatives. So you can do your lower sum and your upper sum, and it lies somewhere in between. So that answer can be negative. So it isn't always the area. It could be the negative area, because this procedure is saying integrate, make a whole mass of the rectangles from A to B, sum them. It's not an S, it's a stretched out S, meaning an infinite number. It's the exact answer when you do that process. Alright, but if f of x is less than 0, this is going to be a negative. So it's going to be, if you like, the negative area. So what are you getting at now? You're getting at the need to actually look at the shape of the graph. Is it above or below the axis? So you can interpret the exact meaning of that definite integral, if you like. So here we are. Here's your problem. Find the upper and lower bounds for 0 to 1 using upper and lower sums. So this is the exact answer, and we want to find it, the exact answer to that middle value that the upper and lower sums approach, which would be the area, except if the curve's upside down, it'll be the negative area. Okay, so pause the presentation there, have a go. You can use, obviously here, technology. Unless they ask you to draw the actual rectangles in, you can, as they do here, you can just escape using technology. So I want you to go through those. You may pause the presentation now and have a go. I'm going to go down here and show you the answers. There are the answers. So you can pause it there and mark it. I'll leave you back up here to start them. Okay, so it's all technology here. Unless asked for a diagram, we just ask for the upper and lower bounds, upper and lower sums, because between them is trapped the exact answer. If we integrate all those rectangles, make a big mass of them, take an infinite number of them if you like, that's the exact answer. This is the exact answer. to this. Okay. Okay, so it's saying find the balance for that, somewhere between this and this. All right, away you go. The answers are down there. I want you to pause the presentation, rewind it, do the problems, and come on. I'm going on now. Okay, so here's what we've found. If f of x is less than or equal to 0 under the axis over an interval from A to B, there it is, then it's minus the shaded area. This is a fundamental theorem of calculus being investigated here. The rectangles are now upside down. This always says sum them. Even if they're upside down, it will sum them. So in this context, you will get a negative value. It will mean minus the shaded area. But the actual answer to the problem will be a negative, because you are summing rectangles that are got negative height, if you like. Okay, come down. Use graphical evidence and known area facts to find these. So you can find the area of this thing here. Right, it's a triangle, half base times height. But the actual value of this will be -4. Right, so you can find the area just using the numbers. But because you're summing rectangles which have upside down, have a negative height, this actual value will be -4. Okay, and again, we're finding the exact value of that area there using circle ideas, a quarter pi r squared. But the definite integral means the sum of the rectangles made as a mass, integrating all the rectangles across that interval. And they would have negative heights, so the answer is actually negative. Watch that. Understand that this is the continuing process of the upper and rectangle sums taken to an infinite situation, if you like. So if they're upside down, this can be negative, and therefore means a negative area, if you like. Okay, I want you to go on now and do the final little set of exercises here. There they are, and there are the answers. So pause the presentation there and have a go. Right, I'm going to move on now and to the properties of definite integrals. And so here we can say, if you're considering upper and lower sums, then if you had two functions added, you could actually say, well, if I did it across both of them, it would be the same as doing one, do its rectangles, and adding the other one's rectangles under it. So you can split them. The integral of the sum of two functions is the sum of two integrals. If you multiply the function by c, then it's just c times the rectangle sum. Okay, so here you can put a negative out the front. If it's a negative of f of x, as we've just seen, it's minus the integral, okay, of a to b, because the function's gone under the axis, if you like. And here you can add up. If you're going from a to b and then from b to c, what does that mean? Let's just draw a diagram here. So if we've got a function and we're going from, let's say, a to b, we're doing it there, and then b to c. Obviously, if you do your rectangle as infinite number there, you'd get that, and do an infinite number there, you'd get that. And obviously, you could have just done it straight across the interval, rather than splitting into two masses, two integrations, could have been one straight across. So, we don't prove these in this course, but they all follow from the properties of sums. That if you have a sum and you multiply each of them by a constant, you'll have the constant times, see in there, you have the constant times the whole sum. You can split it. Okay, I want you to do some work on that. Here they are here. And just using the first information here, and then trying to evaluate these as you go, and see what you think there. And I'll bring up the answers down the bottom here in a minute. All right, so there are the rest of the problems. You have to toggle it forward and then pause it. and then there are the answers down the bottom. Okay, so we're nearly at the end. A fairly long presentation, this one. Remember, it's Hayes, Hayes and Harris. We're down to 2F2 now. So have a go. Pause presentation, have a go. I'm going to move on. Hey, what have I done here? Let's have a look again here. So looking at this, I want you to see that there is a way of finding a definite integral. Now the calculator knows, but we don't know yet. We can find the exact value of that if we can link the function's graph to a known area. But I want to show you on the calculator how to find the exact answer. Then later in this course, we're going to look at how do you get this exactly. How does the calculator actually do that? Alright, so first of all, go to run mode, hit execute, and as you can see when I've got this symbol up there, I'm in the math form of run mode. And here then, what have I done? I've hit options. If you hit the option button, you get this window, and we want to then hit F4 to get calc. Let's just come down a little bit here. Hit F4 to get calc, and if we do, up comes this window, and we want the integral. See that little integral sign there? So we hit F4 again. Oh, and it comes up with a picture for us that we can fill in the values. So if we wanted to do this from the interval A is 1 to 2, we can toggle up and down here with this button, then put the function in, the whole. Very nice. So remember, it's run mode, options, and then we'll just go up there and see that again. Run mode in math format. I'll show you the other one in a minute. Hit options, then calc, so it's F4, and then in calc, there it is, there's the integral sign, and then we enter into the various positions. So if you have run mode in linear form, you don't get this. So when you do that and hit execute, you get the answer. If it's in linear form, so just check that. If you go shift menu, so shift and menu to set up, in run mode you can change it to linear up the top in the first entry. Change it to linear, and then if you do the same steps and hit the integral sign, you actually have to put in that x squared comma bottom limit, top limit of the interval. So that's not as neat, that's not as nice, harder to do. So if you're in linear mode and you hit the integral, you'll need to know that syntax. Function, lower interval, upper, and then the format of the answer is 7/3 in that fraction, the technology way of representing a fraction there. Alright, so you might play around with that. We still have the question, how do we get it exactly? Okay, we can do it with technology. We can match up particular areas. We can use technology. But mathematically, how do we do that? Well, that's a bit of excitement waiting for you later on. But this brings us to the end of Chapter 2 in Hayes, Hayes and Harris, the Introduction to Calculus. So I hope you've enjoyed it. Make sure you do all the problems. And I look forward to seeing you in the next presentation as we move into calculus in more detail. Cheers for now.